This is another famous example called the coordination game. Suppose there are two users, again, you and your friend, and one night you decide that maybe you should go watch a movie. And let's say there are two kinds of movies, action and romance. So again, each player has two choices in the action strategy set, action versus romance movie, for you, player A, and also for player B. Two strategies, action or romance. Now suppose you two decide different kinds of movies, then there's no agreement and you decide not to watch a movie, and you get 0 payoff, so both of you. Okay, this for you, this for your friend, this is for you, this is for a friend. But suppose you both pick the same kind, then you get some strictly positive return, except the returns value are different to you and to your friend. Say you prefer action, so if you two both agree on action movie, then you get 2 units of reward and B only get 1 unit. And conversely, let's say your friend B likes romance movie more than action movie, so if the outcome is going to see a romance movie, then B gets 2 and you get 1. So obviously you both have the incentive to try to reach some kind of consensus. Okay. But you still would like to compete, because depending on what kind of consensus it is, you'll be getting different kinds of payoffs. So again, now we have defined a game, coordination game. The set of players, which is A and B, for each user, there is a strategy set, 2 possible strategies, and the payoff functions basically map action to 2 for A, 1 for B, maps romance to 1 for A, 2 for B, and it maps romance action or action romance to 0 for both players. That's the payoff function. So now we have completely specified this game. Let's understand the behavior here. Now clearly there are best response strategies. For A, if B chooses action, then the best response is action, because 2 is bigger than 0. But if B chooses romance, then A's best response strategy is romance, because 1 is bigger than 0. So now you see that there is no dominant strategy, because the best response strategies for different B's choices will be different. Similarly, B does not have a dominant strategy either. However, we see that their best response strategies actually click, they match. What do I mean by they match? Well, if A chooses action, then the best response by B with respect to that is action. Similarly, if B chooses action, then the best response with respect to that for A is also action. So the action strategy choices by A and B is one that matches. Same story for romance. So you see that these 2 best responses are actually clicking with the 2 best responses respectively by B. And in general, we can define what we call the Nash equilibrium. Basically, it is an equilibrium that describes strategic players' unilateral lack of incentive to move away from this choice. Notice this word equilibrium is not the same as the equilibrium we saw earlier, which used to describe the convergence of iterative algorithm to a particular point. In fact, we later see yet another notion of equilibrium. So more precisely, let's say that there are 2 users. Okay? And user 1 got utility U1, user 2 got utility U2. And user 1 got a strategy set, script A. And user 2 got strategy set, script B. And we say that a particular point, call that A star, and a particular point B star in A and B sets respectively is called a Nash equilibrium if the following definitions are true. First, the first user's utility at this point, A star, B star, will be no smaller than the utility where user 2 sticks to B star and user 1 is free to pick any A in the set of possible strategies. Okay, that's for all A in the set A. This simply says that, hey, if the other player doesn't move away from B star, I have no incentive to move away from A star. And, that's the key word, and at the same time, the other user feels the same way. You too, at this A star, B star, is no smaller than the utility for user 2 if A star remains there and B is free to be chosen anywhere in the set. Okay, so this B can be any point in the set. Doesn't matter. What it says is that for user 2, again, I have no unilateral incentive to move away from B star. If the other player sticks to A star, I'm going to stick to B star. And the key thing is that both statements must be true for the single point A star, B star. That's what we mean by matching best responses. And if so, we call this A star, B star point a Nash equilibrium. It says there's no unilateral incentives to change my strategy away from A star, B star. So in this case, there are two Nash equilibria. The action is a Nash equilibrium because neither A nor B has a unilateral incentive to move away from this choice. And there's another Nash equilibrium, romance. And back to the prisoner's dilemma, this confess is the unique Nash equilibrium. Even though both realize it's better to go there, but there's no unilateral, that's the key word, incentive to move away from this point. Basically, A says, if you don't move, I don't move. B says, well, if you don't move, I don't move. And they both are stuck in this socially suboptimal, unique Nash equilibrium. So we see that Nash equilibria may not exist. Well, both examples we just saw, they exist. It may not be unique. It exists. We saw an example with two Nash equilibria. And none of the Nash equilibria might be socially optimal, maximizing the summation of payoffs, or even be Pareto optimal. However, by a very fundamental result by John Nash in his PhD dissertation at Princeton, he showed that as long as you allow each player to flip a coin and probabilistically decide which strategy to choose, then in that so-called mixed strategy scenario, there will always exist at least a Nash equilibrium. Now back to our power control problem. We said power control is competition, and competition can be modeled as a game. So what kind of game are we talking about here? Well, let's identify the set of players first. Well, that's the logical link or the transceiver pair, there are n of them. Let's identify the strategy space here. It becomes a little more complicated. In the two examples we just saw, the strategy space is pretty simple. It's just two choices. But here is a continuum of the power levels for each user I, such that the target SIR gamma is achieved. Now, as you can see, the strategy space, so defined, is a set of P's that's determined in part by what the other user's P's might be, because that would determine how easy or hard is it for you to achieve the target SIR. So it's through the coupling of strategy space instead of the coupling of payoff function that we see the interference phenomena reflected in the power control game here. Because the payoff function is very simple, you basically want to look at a cost function, that is pi. You want to make this small. So that is the definition of the game. And here are two simple but important facts. Fact number one, you can easily verify for yourself, is that the DPC algorithm, what is the algorithm again? It says that the transmit power for each transmitter I at time t plus 1 is the current transmit power times the ratio between the target SIR and the current SIR at time t. And this goes on for all the users. This actually is the best response strategy in response to all the other players' strategies. Whatever they might be, they are reflected through the SIR value. And by changing my power level this way, changing my strategy this way to the next time slot, I'm basically executing the best response strategy. The second thing you can check is a monotonicity of the strategy space. What do I mean by that? By that I mean that if all the other users make their powers Pj, j not equal to me, I'm user I, smaller, okay, make these smaller, then my strategy space, the set of p's such that the gammas can be achieved, will be bigger. Now this is obvious once I state it, right? Because if you reduce your transmit power, I have less interference, so I have more choices of p, smaller values of p that can still give me my target gamma. And this is what I mean by monotonicity of the strategy space. It turns out that there's a special name for this kind of game, and subject to some technical condition that holds in this case, we say that best response strategies, iterations of best responses, will converge to an equilibrium, to a Nash equilibrium, provided the strategy spaces for all the users are monotonic in the sense that we just described. So we won't have time to go through the proof of that, but this is one way in addition to the optimization method that we'll go through in the advanced material part of the lecture to prove convergence of distributed power control algorithm.